Hi, this is Zubair ibn Kabir. I hope you all are having a very good day. And also, I would like to welcome you to this video lecture series that I'm hoping to upload. And this series will basically deal with the fundamental concepts of signals and systems. Now, signals and systems are basically the foundation of signal processing. I mean, the name signal processing actually suggests that, right? So, before understanding what or how we are going to process, we will have to understand or gain a deep knowledge about what we are going to process. So, the question of what we are trying to process will be basically answered in this particular video. So, uh, the basic foundation of signal processing actually constitute of signals and systems. So there are two parts, signals and systems, and in this particular lecture I will focus on signal itself, and hopefully in a later video I will be talking about systems. So to start off, what exactly is a signal? So if I basically ask you to define signal, then one of the common definitions that I will get is signal is basically a function, right? Function. Now, this definition is actually not full. There is more to this definition. A signal will become a function only if the function has a particular meaning associated with it. So a signal basically has two parts, or I should say that while defining a signal, we can define it to have two distinct parts. The first one is function, and the second one is a meaning associated with the function. So a function will be called as signal only if it has a certain meaning associated with it. So we will be talking about what does it mean that the function has a meaning associated with it in the later part of this video. But at first I want to tackle the concept of function. Now, um, this word function, when it comes to signals and systems, we actually gloss over this word without thinking too much about it. But this function actually has a very important this word function has a significance in the wider spectrum of things. So we will basically start off by defining a function at first. So before defining a function, we will have to have some idea about relations, because functions and relations are somewhat related. And in order to know about relations, we will have to know something about sets and variables. Now, just a disclaimer out here that this sets, variables, functions, relations, all of these are broad terms on their own, and if I want, I can create a playlist just on these individual topics. So it's impossible for me to go in depth of these things right now. But what I'm gonna do is I'm just gonna gloss over, or glide over the concepts that we will be needing for understanding signal. So let's start off with sets and variables. Now, what is a set? A set is basically a collection of things, right? Collection of things. Collection of things. I'm extremely sorry for my handwriting out here. Just bear with me. So set is basically a collection of things. Now, what is the thing? The answer is anything, right? So a set, for example, I can define a set to be a collection of all the furnitures that I have in my house. So for example, I have a bed, I have my sofa, I have my chairs, right, and lots of other things. So this is basically a set which constitutes of the elements or the furnitures that I have in my house. Similarly, I can define a set also to be a collection of numbers. So for example, 1, 2, 3, 4, 5, 6, right? So basically set is a collection of anything and everything. I shouldn't say actually everything, because at the end of the day, sets are bounded. sets are bounded in a sense that sets are bounded by a definition. It can have infinite elements, but those infinite elements will also be bounded by a particular definition. What do I mean by this? So suppose the thing that I have written out here, it's basically I have specified every single element of this set. But there's another way of writing this same set. So I can basically write this set based on its characteristics, the characteristics of the element. So what I can say here is I can basically define something. For now I'm calling it a variable, and I will come back to it what a variable means. So I'm basically defining a variable x, and this x is such that x belongs to, now here we can see that it's all integer numbers, right? So I can write that integers, and also x is greater or equal to 1 and lesser or equals to 6, right? So here what I am doing is I am basically, instead of specifying every single element, I am just defining it by its characteristics, right? The characteristics of the elements of this set B. Now suppose I define a set C, and the definition is something like this, that x such that x belongs to real number. Now out here, if I now ask you to reconstruct the elements of this set, then what would be the elements? The elements in this set C, it can be 1, 2, 3, 4, 5, dot 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 up until what? Infinite, right? So there are infinite amount of elements in this set. But even if there are infinite number of elements in this set, but still this set is defined by a condition, and the condition is that the elements must be a real number. So that's basically what I tried to say, or what I tried to convey, that even if the set has infinite number of elements, but still it would be bounded by some definitions. Okay, so this is basically sets. Now let's come to what variable is. Here I say that x is a variable, right? Now a common misconception that people have is x is basically they basically consider x to be some kind of a box, and this box can hold almost anything, right? So if I ask what's a variable, people basically reply that variable is something that can take the value of anything. But this is actually a wrong answer, especially from a mathematical perspective. Variable is basically a representation of the elements within the set, right? So if I have to say that x is a variable, I also will have to define the characteristics of x such that it fits under that particular set. So suppose if I let's take this example. Let's take B out here. So suppose I say I have defined B to be such in this way, that x such that x belongs to integer, and it is less or equal to 1, sorry, it is greater or equal to 1 and less or equals to 6. So now if I say that what's the value of 6 out here, the value of 6 can't be 7, right? Because here I have defined x to be element of this set B. In fact, we can consider this variable to be a proxy, right? It's basically doing a job of a proxy. So instead of writing every single element, we are using this x to represent every single element of that set. So a variable must have a set associated with it. Now the question comes, okay, when we write an equation, for example, that y equals to x squared, this is an equation. Here we basically say that x can be any value, and the answer is right. Why is it? Because the set that we have defined, even though it's basically not said every single time, but the set that we have defined is basically a set that contains all the real numbers. So if this contains all the real numbers, then x can be any value within that real number, but still x is associated with a particular set, and this is extremely important to understand. A variable is associated with a set, right? A variable is associated with a set, and we can basically understand it. So suppose if I say that y equals to root over x. Now in this particular case, in this particular function, actually this isn't, I mean, we are yet to go into the definition of functions, but in this particular equation, what are the possible values of x? And the answer is x can be any value that is greater than 1, greater than 0, right? Greater or equal to 0, I have to say it, because root over does not accept any negative numbers. So here we can see that x is basically an element of a set which has all the positive numbers only, or we call it natural numbers. Natural numbers, right? So out here in this particular equation, x is a variable of a set which contains all the natural numbers. So I hope up until now it's clear that variables are associated with sets, and we will have to define set at first before we can define a variable. Okay, so we have defined set, we have defined variable. Now let's talk about something which is known as Cartesian product. Now a Cartesian product basically gives us the combination of elements, right? So suppose I have a set A which has 1, 2, 3, and I have another set B which is, let's suppose, 4, 5. Now I want to know what are all the possible combinations, or I shouldn't say combinations, a better word would be permutation, because as we will see that in Cartesian product the order is extremely important. So if I want to know that how many pairs can I basically create, then we will call it a Cartesian product. So we will have to define another set C which will basically have the elements of A, the product of A and B, Cartesian product of A and B, and this will be a set which will hold all the possible combinations or permutations. So 1, 4, 2, 4, 3, 4, 1, 5, 2, 5, and 3, 5, right? So these are all the possible combinations that we can get when we try to unite A and B together. So C is a set, right? C itself is a set. But here we can see that the elements, now we have defined, while defining sets, we have said that set can be a collection of anything, right? So here we can see that we have a first bracket, and inside that we have some values. So what exactly is this? So what are the elements of this set C? And the answer is these are known as ordered pair. Ordered pairs, right? So in a set containing the Cartesian product of two sets, we will have the elements as ordered pair. So what is ordered pair? What is ordered pair? So ordered pair, as the name suggests, that it will have a pair. So basically it can only have two values, only two values. So this is known as the x value, anything which is out here, and this is known as the y value. We'll come what it means that this is the x value and this is the y value later. So it is pair, but it has to be ordered, right? So it must follow a certain order, and the order, as we have described, it's x and y. So when we basically find out the Cartesian product between A and B, in each of the ordered pair, the first element needs to come from A and the second element needs to come from B. So from here, A cross B, or I should say the Cartesian product between A and B, is not the same as the Cartesian product between B and A. This is an important concept out here, and we will have to remember this thing. Okay, so now suppose let's go to relation right now. So we have developed the foundation of we have developed all the foundations that we need if we want to talk about relations. So what is basically a relation? So suppose I have set A, and this set A contains all the natural numbers. actually not natural numbers, let's say that it contains all the real numbers, so minus 1, minus 2, minus 3, dot 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 up until the infinity, right? And then B is also something, also a set which contains all the real number. So now if I want to find out the Cartesian product between A and B, then I will have a set which will contain all the possible combinations that can be formed using this two sets of real number. So as you can imagine that there will be infinite number of combinations, and there will be combinations of every single elements. Well, of every single elements, I mean there will be combinations. So for example, there will be one combination between minus 1 comma minus 1. There will be one combination of minus 1 comma minus 2. So each element will be combined with the element of the other set, right? So each element of one set will be combined with each and every element of the other set. So here we can see that we will find every single combination possible. So from these combinations, and and it contains all the combinations that we can imagine of. Suppose I want to find a combination with a particular characteristics associated with it. What do I mean by this? By this I mean that suppose I want to find, or I want to separate out only those combinations whose x values will be, or I should say whose y value, let's suppose, will be equal to the square of their x counterparts, right? So here the elements of A are represented as x, and the elements of B are represented using the variable b, using the variable y. So here we can see that the value of y is actually dependent on the value of x. So that's why here x is the independent variable because it works independently, and y is the dependent variable, right? So this x value can be anything. It can be 1, it can be 2, it can be 3. But this y value, it can't be, suppose it can't be 3, for example, right? It has to be 1, or it has to be 4, right? So only the squared values are possible in case of y, and this value will depend on x. So this is an independent variable, whereas this x is a dependent variable. Okay, so now suppose I want to find all the ordered pairs, that follows this particular relation. This is where relation comes from, right? So basically relation tells us about the connectivity between the ordered pair, okay? So when we basically write down an equation, or when we write down a function, y equals to x squared, suppose, what we are actually trying to find out is basically a set. We are trying to find out a set, suppose set C, which will have all the ordered pairs that is possible when we combine two sets A and B, and this A and B contains all the real numbers, right? Let's just write out here real numbers, right? So when we find out the Cartesian product of A and B, the Cartesian product of A and B will have infinite combinations, but out of those infinite combinations, I am basically trying to find out only those combinations which has this particular characteristics associated with it. So basically C, if we consider C to be a set of C to be the set of the values that actually that solves this equation, then we can say that C is basically a subset of the Cartesian product of A and B. So this is basically a relation. So a relation can be anything, right? So the best way of representing a relation is to draw a graph. So a relation can be of any shape. So this is, for example, y equals to x squared. This is basically y equals to x. So yes, so basically drawing graphs and solving them are the easiest way of solving equations or solving relations in general. Okay, so I hope now it's clear what relation is. Now the graph of relation can be anything, right? So for example, it can have something like this. Okay, now out here, if we look at this, we can see that at this particular value of x, so in this axis we have x-axis and this axis y-axis. For this particular value of x, let's suppose a, we are actually getting two values of y, right? So let's suppose this is y1, this is y2. So basically we will have one value of x and two values of y1 and y2, right? So these are basically the possible ordered pairs. Now this is possible in case of relation. Now why? Because we are basically, as the name suggests, I mean, I don't have to go in depth of the meaning of relation. Relation means, you know, any sort of connectivity. So the connection between these two sets or the combination of these two sets can be anything. So there is no prohibition when it comes to relations, right? But as we will see, and in fact we will see it now, function has certain prohibitions related to it. So in case of a function is basically a relation, but the function will have only one unique value of y for every value of x. So what do I mean by this? So in case of relation, so basically an example of relation would be, suppose y square is equal to modulus of x, right? So from here we will see that y is actually plus or minus root over x. So this y is actually plus or minus root over x. So here we can see that for one single value of x, so for example if I say x equals to 4, then my y value will be plus 2 and minus 2, right? So for one x value I'm getting two y's. But in case of function, this is prohibited. We will have only one y associated to x. So now in case of function, it is possible. So for example, let's see function out here. Now it is possible that one y value, so suppose let's just write its yeah, so basically just one y value. So let's suppose y1. This y1 can be associated with two x values. This is possible in function, but what is not possible is that one x value is associated with two y values, so y1 and y2. Now this is not permissible in case of function, right? So what it means is that a function can never be something like this, because here for one particular x we are having two values of y. So I hope it's clear that relation basically is relation between the combinations or some sort of connectivity between the combination of the two sets which contains the real numbers. And function is basically a more constrained definition of a function, of a relation. I won't say it's a constrained definition of a relation, but it's basically a more constrained manifestation of a relation. Okay, so at the end of the day, a function is a relation. So we can say that all functions are relations, but not all relations are functions. Okay, so now with that gone, let's now talk about what it means that a signal will be something meaningful. Okay, now I will at the end of the video I will basically try and connect all of the things that we have learned so far. But before that, let's talk about what it means that something meaningful. So suppose a function can be a sine wave, right? This is a function. This is a function at the end of the day. This is also a function. mm, this is also a function, and then this is also a function, because in every single case for one value of x we are just getting one value of y. uh, yeah, but yes, so basically the thing that I was telling earlier, in case of this particular function we can see that for two values of x we are getting the same value of y, right? So this is permissible in case of functions. Okay, so now these all of these things are functions. All of these things are functions. This function will only be called a signal when we define what this function actually means. So once we define what this y and x means, so suppose in this x-axis I am defining it as time, and in this y-axis I am defining it as voltage. Now once I have associated a meaning with the function, now this function is called a signal. So a signal is basically a meaningful function, right? So if the meaning of x and y's are defined in a function, then that function is a signal. And that basically defines, or that basically says why a relation can never be a signal. Because suppose I have something like this. Suppose I say that I'm plotting the value of voltage in y-axis, and I'm plotting the value of time in x-axis. And suppose instead of a function I have a relation, right? So the most simplest form of relation is this curve. So now if I ask you that, is this curve, which is a relation, this is a relation, now does this actually make sense in a physical world? I mean, is it possible that suppose I'm measuring the voltage across this circuit, and at a certain time, at a very particular time, I am getting two values of voltage? Is it possible? In real life, it's impossible that for a certain time, or for a very particular time, we will have two values of something. And the same thing, if for example instead of time here we have space. Now this is also not possible that that at a single space, or at a defined space, we have two particular values associated with that space, with that particular space, right? That's not physically feasible. So that's the reason that this relation is not considered when it comes to signals, because signal is something physical. Signal is physical, right? Signal needs to have a physical meaning attached to it. So the question is then, doesn't this sort of curve actually appear in when we are dealing with signal? The answer is yes. So especially this curve in the first quadrant, this sort of curve actually appears quite often in signals. So in that case, what we say is that we discard this portion. So we say that this portion does not exist, right? So for example, this is an example of y equals to plus or minus root over x. So when suppose I have a signal, signal which is kind of like this, so what we say is that this minus sign is not feasible out here. It's not physically feasible. So what we do is we basically cancel or ignore this minus sign and write it as y equals root over x. So when we do it, what we have is just this curve, right? And at that point in time, once we define this thing, so again it comes to how you define the set, right? So when it comes to this different definition, now the domain and range, that's another concept altogether of function, and I hope that everybody has taken the courses of function, and especially in their high school and before that. So the domain and range, the domain remains same for these two functions, but the range changes drastically, right? The range is basically the output, if you want to say in that particular way. So yes, at this point in time, this relation actually changes into a function, right? So we have basically converted this relation into a function. So I hope that you have understood the fundamentals of signals, and Also, you have learned that why relations can't be known as signals. So yes, that hopefully you have understood it intuitively, and that was my goal in this video. And that's all for today. Hope to see you in a next video. Thank you.